values it can take. So nature is fascinating because of that. You might see patterns in this range of values, you might see patterns in this range of values only. So what are the scales? In one of them, the scale will be very, very small. In the other one, the scale will be very, very large. So that is the beauty about nature. Patterns, when they are seen, you will see that they may be scaled down or they may be scaled up. Now what is wind? You say that it is a windy day. What is wind? Let us take this. The earth's surface is very hot. What happens to the air very close to the earth's surface? It gets heated up, and what happens to the air? It moves up and falls at 30 degrees north and 30 degrees south. So that is a circulating, huge circulating pattern. Now imagine the equator is 0 degrees. So 1/3, no, not exactly 1/3, a little more than that. So you see that if this is the equator, you see that the air moves up and falls down where? At 30 degrees north and 30 degrees south. How many thousands of kilometers the air circulates? Now think of this. What is the scale of that circulating pattern? That scale of the circulating pattern is thousands of kilometers. Now if you do similar experiment here, I showed you the rectangular box. What is the height of that circulating pattern? Height of that circulating pattern may be a few millimeters. So that is what I am exactly referring to here. The scales that you see in nature can be very small. The scales that you see in nature may also be very large. But the underlying mathematics that you see, it unifies everything. Okay, so it not only represents the ones at the small scale, it represents the ones at the large scale also. So it's a unified treatment of many of these problems. So this is what you have. I only say this, I'll just take 10 more minutes, okay? The mathematics that we use, are you doing partial differential equations? Okay, so the mathematics that we use to model these problems in different scales, whether it is small scale or large scale, the mathematics that we use to model these differential equations, they are partial differential equations. Most of the times when we model these processes, the partial differential equations are like the heat equation, or are like the wave equation, or are like the Laplace equation. One of these, you have done classification of PDEs. Partial differential equation. Have you done classification? Parabolic, hyperbolic, elliptics. Parabolic heat equation, hyperbolic wave equation. What is it? Elliptic. What is an example? Laplace equation. Okay. Poisson equation. Helmholtz equation. These are all examples of elliptic equations. So the equations that we use in order to model all these different processes that I mentioned to you, they are all partial differential equations. Either they are like the heat equation or the wave equation or the Laplace's equation. Okay, so this is what you have. Don't worry too much about these equations. Okay. You can make some simplifications. Okay, what did you observe? In the model that I showed you, in the patterns that I showed you, what did I see? What I saw was, I found the circulating patterns. Okay, when the entire fluid is circulating like this, what I see in this cross section will be the same as the next cross section. Is it right? What I see here is circular. If I see here, that is also circular. If I see somewhere further, that is also circular. So what is the meaning of that? The meaning of that is, there is no need to see the variation with respect to one coordinate. It is repeating itself. Is that clear? So I can simplify my partial differential equations, reduce the number of independent variables by one. So hence, in literature, you will find three-dimensional, two-dimensional, one-dimensional, okay, many things. So these are all because of what we observe in these problems, okay. They are simplifying things. So that's what has been done here. Don't worry too much, okay. This will not come for your exam, okay. Now what you do is, you have to scale your equations, obviously. Why do you need to scale? Suppose I have something which is seen in very less space. Which is the best? Suppose I don't see this. Suppose I don't see this. What should I do? See, I'm sure you have grandfathers or even your parents. They can't see something which is nearby. Okay, I also cannot see. So what do? Okay, you have to have that appropriate lens. So you have to magnify. Is that clear? So scaling is something like that. When something is near, you are unable to see, you have to magnify. When something is very large and you have to see, what should I do? I have to contract. Is that clear? Scaling is essentially that. So that is the reason why in equations you do the scaling. Okay. So some scaling is done, then we make use of some equations, some ratios are formed which are called as numbers. Okay, don't worry. So I know my maths, so I'll find out the solution. Okay. So I'll see the stability of the system, stable or unstable, or whether it goes to turbulent regime and so on. So I'll do all this maths. Okay. I'll get all the results. I'll solve. I'll get all the results. Very complicated results. It looks like, but it is not complicated because of the type of computers that you have. You have laptop with you now. Okay. So laptop can do everything. See, in one particular batch, we even completed the computer lab for our MSc students using their own mobile phones, because they could download Python in that and complete all the exercises, because there are some problem with the lab. So that is the power of computing these days. So you are able to do a lot of things with these things. So all these things are possible. Okay, some beautiful results are here. What was my talk? Title of my talk? Remodeling. Okay. Now the question is, in both the problems, the Taylor-Coet flow and the Rayleigh-Benard convection, the question is, I saw a cylinder. I have two concentric cylinders, and between them I am seeing a number of circulating patterns. Okay, I am seeing a number of circulating, one above the other. If I take the rectangular one, I am seeing circulating patterns one next to the other. Is that clear? Now suppose I say that I have a cylinder whose height is 1 meter, and I ask you the questions, how many cells will form? Okay, how many cells will form? Is it theoretically possible, mathematically possible to predict how many cells are formed? Okay. In the case of Rayleigh-Benard convection, is it possible to predict for the given size of the box how many cells will form? Okay, horizontally, that is. So for that, I will have to convert this infinite dimensional problem into a finite dimensional one. So when I go from the infinite dimensional to the finite dimension, then I can obtain a formula to find out how many cells are formed within a finite dimension. Okay, that is these are modern questions. What were earlier questions? Earlier questions were, if suppose I rotate the two cylinders, I get the circulating pattern. If I heat a box from below and cool from above, I get circulating patterns. But what are the modern questions now? Recent questions. The recent questions which we have to ask is, for a given finiteness in the dimension, how many such cells will form? So, from the infinite, I'll have to render the problem finite and then give a formula for number of cells between the two cylinders or between the two plates of the rectangular box. Okay. See, these are all physical problems. The mathematics, the underlying mathematics for these physical problems, they are all manageable. The partial differential equations that you are studying in your classes, you can use them for all these things. Okay, the numerical methods that you do, you can use them for all these problems that you do. Okay, so the mathematics is not something very, very difficult to understand insofar as these physical problems are concerned. You may call it physics in one place, it is mathematics in yet another place. Okay, so that is the reason why they say all sciences are seamless. Okay, there is no real distinction so far as these sciences are concerned. So I'll just stop here.
Any question from the gathering? Do you have any question?
Nice children. Everywhere.
We want teachers like you.
Yeah.
Really do very well.
Thank you. See, some of you, one reason why all of us are here is to tell you that one thing is to let you know that there are institutes like IMS, to let you know that there are places like IITs, there are places like, say, Christ University, there are different places. Okay, what sort of activities go on there and how many people can come together irrespective of their affiliation. Okay, they can come together, you will get to know. So make full use of this opportunity, discuss with them, okay, and find out what you can do beyond your MSc. Okay, can you go to IMS, for example? What are your interests? What are your orientations? Okay, can you go to IIT Guwahati, for example? Can you go to Christ University? Can you go abroad? Why not? Something like that. So speak to people and you'll get to know many things. Only when you speak, you get to know many things. So my best wishes to all of you. Thank you very much for the patience.
Sir, before we conclude, I have two questions. One is, when we are from infinite domain to finite domain, how difficult it is to convert a problem from infinite domain to finite domain?
Uh, See the question, there are two questions which are normally asked. One is what is zero, what is infinity? Okay. So if you want to answer this in say simple terms, I'll take you to the story of Tenali Ramakrishna. Okay. So Tenali Ramakrishna was given a small stake, and the king told him that you have to make this stick short without cutting it. So what did Tenali Ramakrishna do? He took a longer stake and kept it next to the smaller stake. So which is zero, which is infinity now? Okay, so zero and infinity, they are relative. Okay, so now if you take 10 to the power of minus 4 and you say take 10 to the power of plus 4. So for a physical problem, 10 to the power of minus 4 can be 0. 10 to the power of plus 4 can be infinity. So it is all very relative. Okay, so when it comes to say handling problems of an infinite dimension and a finite dimension, in physical problems like the ones which I am mentioning to you, it is only the range of parameters which now become some finite number. That is all. The handling of the problem will be more or less the same. But you will have to redefine a few things which can be done.
The next one is what are the numerical techniques we have to solve such problems?
See, normally what happens is in our problems, we simply take, let us take viscosity or thermal conductivity, where we assume that the viscosity and thermal conductivity does not vary. The fluid's viscosity and thermal conductivity is a constant. We assume that. But practically speaking, there must be some variation of these quantities with temperature. So when we assume viscosity and thermal conductivity to be constant, what is the advantage? Mathematicians are very clever. Okay, they want to always have problems with constant coefficients. Okay, why do we want to have problems with constant coefficients? Because it is easy to solve. Complementary function, particular integral. Suppose I give you a variable coefficient problem. What is the difficulty? I have to convert again that problem to a constant coefficient problem. Can I do that for all problems? Cauchy equation? Yes. Legendre different. Okay, some problems I can convert to constant coefficients. So when you have these properties of fluids which become variables, the differential equations that we try to solve, they become variable coefficients. So when they become variable coefficients, then all the complexities will arise. Maybe you will get special differential equations like Bessel, Legendre, and so on. Okay, so that it is only because of difficulty in handling problems that simplifications are done. But mathematical sophistication is such, we could not have dreamt that topology can be used in solving differential equations. What is happening today? You are seeing very complicated partial differential equations, non-linear, linear, variable coefficients, all of them being solved through concepts of topology. What do we generally understand when classes go on? You feel that the differential equation and topology, analysis, algebra, they are all disjoint topics. That's what you feel. But what is happening today? Computers have also aided in the process. So don't think of topology and differential equations as being unconnected. One can connect all that. So the connection, see, when you are doing your master's program, you should try to find the connections between different topics. Then only your study becomes more meaningful. Okay, thank you very much.
Any other question? Thanks for your wonderful lecture, sir. We are very thankful to you. And we will break for tea. We will assemble back at 12:50. Okay? Thank you.
For faculty, faculties and speakers to assemble in boardroom.
Happy